This is Group 15's Physics Video Lab Report 2. Our experimental question and hypothesis in this experiment are as follows. Our question was, how does the viscosity of a solution medium affect the resistive forces on an object? How does that resistive force affect the terminal velocity? Does it make it higher or lower? We hypothesized that the higher the viscosity of the solution medium, the greater the viscous resistive force, and therefore the lower the terminal velocity. This means that the terminal velocity would be reached in a shorter amount of time, and the object would move much slower through the medium than a less viscous solution. Our experimental design and procedure is as follows. We chose 4 different solution mediums with different viscosities, those being air, water, dish soap, and corn syrup. Then we took a metal ball bearing and dropped it from the height of the 50 millimeter graduated cylinder for each solution medium. Then we recorded a video clip on an iPhone of the metal ball bearing going through the solution until it reached either the bottom of the table or the graduated cylinder. Then we used tracker software to construct a velocity and an acceleration graph for each trial completed. Then we used those graphs to deduct where terminal velocity occurred, to see which solution medium offered a higher or lower terminal velocity. Finally, we used our physics knowledge to analyze what viscous forces do in terms of velocity, to see if a higher viscosity solution slowed down the terminal velocity. These are our system schemas and free body diagrams for each of the trials completed. Our system schemas all look the same, but the only difference is the solution medium. There is a system schema for air, water, dish soap, and corn syrup. Each system schema has the bead, the ground, and the solution medium in the system. The bead and the solution medium have contact force, the bead and the ground have gravitational force, and the solution medium and the ground have contact and gravitational force. Our free body diagrams show first the air resistance is much lower than the force of gravity because when the ball is first dropped, the air resistance is not as great and the gravity is pulling it down. The second free body diagram shows that the air resistance is a little bit greater, but still not equal to gravity because it's right when the ball starts to move, so the force of gravity is still stronger. Finally, the air resistance and the gravity do equal each other because that is when the ball reaches its terminal velocity, and that means that the air resistance and the force of gravity would be equal. Here's the example of our video data for water, dish soap, and corn syrup.
Here are a few sample graphs. On the left, we show the position and velocity versus time graphs for the metal ball dropping in dish soap. For the position graph, the curved slope shows an acceleration from the drop, and when it becomes linear, that represents when it reaches terminal velocity. On the right, we show the relationship between viscosity and the medium, with the corn syrup with the highest and air being the lowest. The next graph shows terminal velocity versus the medium. The more viscous the solution, the lower the terminal velocity will be.
The independent variable in this experiment was the different viscosities of each solution, and the dependent variable was the terminal velocity of the metal ball bearing going through that solution. We measured the impact of these variables by using tracker software and constructing velocity and acceleration versus time graphs, which could then tell us the terminal velocities of each solution. After we found this information, we could see the effect of the viscosities on velocity, and we saw if a higher viscosity had an effect on the terminal velocity or not. On the left-hand side of the slide are the different viscosity values for all of our solution mediums used, and you can see that air is the least viscous and corn syrup is the most viscous.
Utilizing the graphs produced from our data, we were able to find the terminal velocity for each medium. With corn syrup and dish soap, it was very clear as the velocity reached a constant. However, with air and water, it never reached terminal velocity, but we were able to estimate the value using the graph.
So we use this equation to solve the proportionality constant for each trial conducted. We use a radius of value 0.005 meters, which was the radius of the metal ball bearing. We then used our calculated terminal velocity for each trial, and all the other values were known constants, and the force we used was F equals mg, and the values we got are on the left. The resistive force that we investigated was the viscous resistive force. This compares with macroscopic friction because both of the forces function to slow down a moving object and to offer resistance to that moving object. Viscous force contrasts to macroscopic friction because frictional force is independent of velocity, as you can see in the equation on the right, while the viscous force does in fact relate to velocity. And velocity plays a role in the viscous force as shown in the equations on the right. Our findings suggest that the higher the viscosity of the solution, the lower the terminal velocity will be. We ranked the solutions in order of viscosity based on the proportionality constants that we found, and then we compared how that matched up with the terminal velocities that we calculated. And our hypothesis ended up being correct because the solutions with higher viscosities had lower terminal velocities than the solutions with lower viscosities.